9.3 Air Standard Diesel Cycle Analysis. The Air Standard Diesel cycle is modeled as a closed system. We neglect the changes in kinetic and potential energies. Using the energy balance equation, we got the following heat transfer relations. Q23 is the heat addition process at constant pressure. The specific enthalpy difference between state 3 and 2. Q41 is the heat rejection process at constant volume. The specific internal energy difference between state 4 and 1. The net work of the cycle can be expressed as the net heat added to the system. That is Q23 minus Q41. The thermal efficiency is the net work of the cycle divided by the heat addition. So the thermal efficiency is expressed in terms of the specific internal energy in state 1 and 4 and the specific enthalpy in state 2 and 3. The compression ratio R is V1 over V2. The diesel cycle is characterized by a new quantity called the cutoff ratio. We define the cutoff ratio R sub C V3 divided by V2. So V3 is the volume here, V2 is the volume here. So it is the ratio of the volume after and before the combustion process. The property of the state can be calculated with a cutoff ratio. Going from state 2 to state 3 is a constant heat addition process. Using the ideal gas law, we can write this one is M2, this one is M3. Mass remain constant. It's a constant pressure process. P2 equals P3. R cancels out. So T3 equals V3 over V2 times T2. This is what we have here. And V3 over V2 is the cutoff ratio. The temperature at state 4 can be determined from VR4. The relative specific volume at state 4. If we know temperature at state 3, we can determine the relative specific volume at state 3. The relative specific volume at state 4 can be written V4 over V3 times VR3. And divide the equations by V2 and multiply by V2. We have the same equations. And process 4.1 is a constant volume process. So V1 equals V4. V1 over V2 is compression ratio. V2 over V3 is the reciprocal of the cutoff ratio. VR3. So from VR3, we can get VR4. And from VR4, we can get the property at state 4, including the temperature. Example 9.2. At the beginning of the compression process of an air standard diesel cycle operating with a compression ratio of 18. The temperature is 300 Kelvin and the pressure is 0.1 megapascal. The cutoff ratio for the cycle is 2. Determine the temperature and pressure at the end of each process of the cycle, the thermal efficiency, and the mean effective pressure in megapascal. So this is an air standard diesel cycle. The piston cylinder system contains air in a closed system. air is considered an ideal gas. We are neglecting the changes in kinetic and potential energies of the system. We should know how to sketch the air standard diesel cycle on the PV and TS diagram. I'm going to begin with creating a table with properties in each state. The main goal of analyzing the air standard diesel cycle is to acquire the thermal efficiency. We don't need to know the properties H1, U2, U3, and H4, but we will determine the rest of the unknowns. Let's begin with state 1. At state 1, the temperature and pressure are given. Pressure 0.1 megapascal, temperature 300 Kelvin. So we can fix the state. See table A22. At temperature 300 Kelvin, internal energy is here. This is U1. So U1 is 21407 kilojoule per kilogram. And we don't need to know H1. At state 2, we are not given any properties. But compression ratio R is given. So compression ratio R is V1 over V2, which is 18. Going from state 1 to state 2 is an isentropic process. For air under isentropic processes, we can use the relative volume ratio as we know the compression ratio. The compression ratio R equals V1 over V2. It is equal to the relative volume ratio. So we can solve it for VR2. We also need VR1 at state 1, the temperature 300 Kelvin. At 300 Kelvin, this is VR1. VR2 is 34.51. So see the tables. Find where the relative specific volume 34.51 falls. So it is between these two numbers. So do the interpolations with VR2 to determine the corresponding temperature and enthalpy. So determine T2 and H2. And T2 is 898.3. H2 is 930.98. Now at state 2, we know the temperature. We also want to determine the pressure at state 2. We know that mass remains constant during the process. M1 equals M2. Using the ideal gas law, M1 is PV divided by RT1. M2 R cancels out. P2 is P1, V1 over V2, T2 over T1. P1 is 0.1 megapascal. V1 over V2, compression ratio, 18. T2, T1. So P2 is 5.39 megapascal. At state 3, we know the process 2-3 is a constant pressure process. So P2 equals P3. The cutoff ratio is V3 over V2. Cutoff ratio is V3 over V2, which is 2. Mass remain constant during the process. Using the ideal gas law, it's a constant pressure process. P2 equals P3. R cancels out. V3 over V2 is the cutoff ratio. T3 1796.6 Kelvin. For air, the enthalpy is a function of temperature only. At state 3, we know the temperature, so we can determine the enthalpy at state 3. So the temperature 1796.6 is between these two. Do the interpolations to determine enthalpy. The enthalpy at state 3. At state 4, we'll use both the compression ratio and the cutoff ratio to determine the temperature at the final state. From the temperature at state 3, we can determine the relative specific volume, VR3. From VR3, we can determine VR4, which is V4 over V3 times VR3. And multiply the equations by V2 and divide by V2. V1 equals V4. Process 4.1 is a constant volume process. V1 over V2 is the compression ratio. V2 over V3 is the reciprocal of the cutoff ratio. At temperature T3, VR3 is 3.97. VR4 is calculated 35.73. The relative specific volume 35.72 falls between these two numbers. So we can determine the temperature and internal energy at state 4. And mass remain constant during the process. Using the ideal gas law, constant volume process, R cancels out. The pressure at state 4 is 0.3 megapascal. Now we can determine the thermal efficiency. The thermal efficiency can be expressed. We have all the values for the thermal efficiency. Thermal efficiency of the air standard diesel cycle is 0.578 or 57.8%. The mean effective pressure can be written, and V2 over V1 is the reciprocal of the compression ratio. And using the ideal gas law, the specific volume can be written. Now put the values in. The mean effective pressure is 0.76 megapascal. The higher the mean effective pressure, the greater the net work it produces.